Hi class, today we're going to look at section 4.5, which is on exponential and logarithmic equations. So this section mostly focuses on how to solve problems that feature logarithmic or exponential parts. So first we're going to look at exponentials. So some exponentials can be solved by using the fact that exponential functions are one-to-one. So what this means is that since they have a unique output for every input, that we can undo them to look at what the solution would be. So for example, if we were to have a to the x equaling a to the y, this would imply that x equals y. So for an example, we're going to solve the exponential equation for x. So if we have 4 to the x equaling 64, well, so we're going to look at 4 to the x equals 64 is the same as 4 raised to the 4th power. So therefore, x equals 4. And here, we're secretly taking log base 4 of both sides. That's what this step is, but since we can see that it's 4 raised to the x and 4 raised to the 4, that means that we can simplify to x equals 4. So you don't always have to show that you're taking log of both sides, but if you want to, that also is good. And then if we also can look at 5 to the 2x equals 5x to the minus 1. And then again, we're secretly going to take log base 5 of both sides, and we end up with 2 to the x equals x minus 1. So x equals minus 1. So I'm going to illustrate what this point down here is doing. So if we take log base 5 of 5 to x, okay, so we know that with these exponents, we can bring them down. This is just a side note. This is not necessary all the time. I just want to explain what's happening so you'll understand. So then we end up with 2 to the x log 5 of 5 equals x minus 1 log 5 of 5. Well, this is 1, and so is this. So that way we get 2 to the x equals x minus 1. So since it's 1-to-1, we don't need to show these steps all the time. We can just quickly write it down. So now we need to develop ways to solve equations when they are messier than the examples above. So I'm going to give us some guidelines for solving exponential equations. So first, we're going to isolate the exponential expressions. On one side of the equation. Two, we're going to take the logarithm of each side. Then, using the law of logarithms, we're going to bring down the exponent. And then 3, we're going to solve for the variable. So we're going to look at an example. A lot of this video is looking at examples, just so y'all know. All right, so we're going to consider 3x plus 6 equaling 10. So if we take the log of both sides, so log 3 of 3x plus 6 equals log 3 of 10, then this gives us x plus 6 equals log base 3 of 10. And then we can bring this 6 over. And so we have x equals negative 6 plus log base 3 of 10. And I'm going to leave it like this because when you take y'all's exam, you won't be using a calculator, so you'll need to leave it in this log form like this. So I'm going to do a lot of the examples, some of them like this and some of them using a calculator, just so y'all can get a sense of how it works for both of them. But always, even when using a calculator on your homework, bring it to this form before you just plug in a calculator. Okay. And then the next example. Going to solve the equation. 8e to the 2x equaling 20. So our first step is going to be dividing each side by 8. So we're going to have e to the 2x. This equals 20 over 8, which equals 5/2. And so then we're going to take the natural log of both sides. So the natural log of e to the 2x equals the natural log of 5/2, which then we are able to just have 2 to the x equals the natural log of 5/2. And now we can divide by 2. We get x equals the natural log of 5/2 over 2. And if you were to plug this into a calculator, this would be approximated as 0.458. Okay, now we're going to look at a specific type of problem now. We're going to look at an exponential equation of quadratic type. What this means is we're going to look at something like e to the 2x minus e to the x minus 6, all equaling 0. So this is of quadratic type because the exponents are all instead of using x, we're using ex. So we have, with rewriting, because we can pull out exponents, we have ex squared minus ex minus 6 equaling 0. You see how this is very similar to as if we just had like x instead of ex, it would look like a quadratic polynomial. Well, we can factor similarly. So we can look at e to the x minus 3 times e to the x plus 2. Because if we factored this out, this equals 0, we would end up with this original equation above. So now we have two cases. We have case 1, which is ex minus 3 equals 0. Or we have case 2, which is ex plus 2 equals 0. So then let's solve for case 1 first. We will get e to the x equals 3. So x equals the natural log of 3. And then here in case 2, we'll have e to the x equals negative 2. And then we'll have x equals the natural log of negative 2. But here, negative 2 is not in the domain of ln of x. So it does not have an output. So this lets us know that case 1 is the correct case. This is the one that we know works. So therefore, x equals the natural log of 3. So with these, you will have extra cases sometimes, and they don't always work. There's only one solution here. Okay. So another example. This time we're going to solve 5x e to the x plus x squared e to the x equaling 0. So here we can factor out an x e to the x from each equation. So we'll have x e to the x times 5 plus x equaling 0. So since e to the x does not equal 0 for any x, we can ignore this number. We can divide it out. So that means we end up with an x, 5 plus x equaling 0. And so the reason we can divide this out is because we are never dividing by 0. So it's like a legal move to do. Okay, so therefore, x equals 0 or x equals negative 5. All right, and now we're going to move on to logarithmic functions. We're going to solve the equation. Log of x squared plus 1 equals log of x minus 2 plus log of x plus 3. So our first step is going to be using law of logs here. So we're going to end up with log of x squared plus 1 equals log of x minus 2 times x plus 3 And now we're going to raise each side by 10. So we have 10, because again, this is log base 10, because this is our common logarithm. So then we end up with x squared plus 1, x minus 2, x plus 3. And then when we FOIL this out, we end up with x squared plus 1 equaling x squared plus x minus 6. And now we can subtract an x squared plus 1 from both sides, and we end up with 0 equals x minus 7. So x equals 7 is our answer. So now I'm going to give us some guidelines for solving logarithmic equations. So first, we're going to isolate the logarithmic function. On one side. 2, we're going to write in exponential form or raise the base to each side of the equation. And then 3, we're going to solve for variable. So for an example, we're going to look at log base 2, 25 minus x equals 3. So if we do 2 raised to the log base 2 of 25 minus x equaling 2 cubed, this will give us 25 minus x equaling 8. So therefore, x equals 17. Okay, and then another example. Eight plus 2 log of 5x equals 16. So first we need to subtract 8 from each side. So we end up with 2 log 5 of x equals 8. And then we're going to use, now we're going to divide by 2 on both sides, and we're going to get log of 5x equals 4. And now we're going to raise each power we're going to raise each thing. It's a hard thing to say, but we're basically having 10 getting raised to this and 10 getting raised to the 4th. I'm not sure exactly the words that used to describe this process. I always say I'm raising it to the 10th, which is exactly the opposite of we're doing. We're having 10 raised to it. Sorry for the kind of confusion. But here, if we have 10 raised to the log 5x and 10 to the 4th, that will give us 5x and then a 1 with 4 zeros behind it. 1, 2, 3, 4. And now we're going to divide by 5, and we end up with x equals 2,000. And then another example in this, on this material. So we're going to look at log of x plus 2 plus log of x minus 1 equaling 1. So here we're going to use law of logs, or LOL, and we're going to get log of x plus 2, x minus 1, all equaling 1. And now we're going to exponentiate both sides. That's the word, exponentiate. It's been a long week. All right. So then we end up with 10 log x plus 2, x minus 1, 10 raised to the first. So we get x plus 2, x minus 1 equaling 10. And then, so now we're going to FOIL out, and we end up with x squared plus x minus 2 equals 10. And now we're going to subtract 10 from both sides. So we end up with x squared plus x minus 12 equaling 0. And now we're going to refactor this quadratic. And this ends up being x plus 4 times x minus 3 equaling 0. So now we need to check if our solutions are defined. So first we're going to look at we're going to look at 3. I'm going to check that 0. So if we look at all the way back to the top, log of x plus 2 plus log of x minus 1 equaling 1. If we plug in 3, we get log of 3 plus 2 plus log of 3 minus 1, which is log of 5 plus log of 2. So these are both defined because 2 and 5, oh, that was really messy. Okay, so 2 and 5 are in the domain of log of x. So that means we're good with 3. So now we're going to check negative 4. So log of x plus 2 plus log of x minus 1. So then we'll have log of negative 4 plus 2 plus log of negative 4 minus 1. Well, now we end up with log of negative 2 plus log of negative 5. So here, negative 2 and negative 5 are not in the domain. So negative 4 is not a solution. So that means x equaling 3 is our solution. All right, now we are going to look at an application example. Okay, so if I naught and I denote the intensity of light, before and after going through, whoops, a material and x, the distance in feet. The light travels in the material then according to the Beer-Lambert law, we get this equation, -1/k, the natural log of I over I naught equals x, where k is a constant, depending on the material. Okay, so this kind of light is, or this kind of problem, we're looking at how strong a light stays after passing through a material. So if we were to shine a flashlight through a piece of paper, it would be pretty strong still. But if we were to try to shine a flashlight through like an entire swimming pools of water, it might be kind of hard to see it on the other end. So different types of materials. So if we're going to now, for our first part, we're going to solve for I. So if we take this -1/k, the natural log of I over I naught, so our first step is going to be multiplying by -k on both sides. So then we have the natural log of I over I naught. This equals -kx. And now we're going to exponentiate both sides. So then we have e, the natural log of I over I naught equals e to the -kx. And so then the left-hand side simplifies into I over I naught equaling e to the -kx. And now multiplying both sides by I naught, we end up with I equals I naught e to the -kx. And this might look kind of familiar because this, if we think of the amount of money we have after a certain amount of time, equaling our initial amount of money, e to the RT. In this case, our R is -k, our time is the distance we're going, our I naught is our principal, and our I, the intensity of our light, is the amount of money we end up with. In this case, we're losing intensity, which is why we have a -k, but with money, we end up gaining money through interest. So these equations are very similar. Get rid of our interest one. Oh, and y'all didn't realize that was the continuously compounding interest formula from previous lectures. Okay, so now we're going to solve for k equals 0.025, I naught equaling 14 lumens. Right, so we're going to find the light intensity at a depth of 20 feet. So this is in a pool. I forgot to write that down, but yeah. Okay, so we're going to have I equals I naught e to the negative kx. Now we're going to plug in all of the values we were given. So we have 14 e to the negative 0.025, whoops, and then 20 feet for x. And so plugging this into a calculator, it is approximately 8.49 lumens. Notes are sticking together, sorry. Okay, and now we're going to look at another example, one last example actually for this video. We're going to look at compound interest again. So recall that if we compound n times a year, our equation is A equals P, 1 plus R over N, NT. And if we continuously compound, our equation is A equals P E R T. So our example, we're going to find the term for an investment to double a sum of $5,000. Remember, this is our principal. Oh, this is okay. This part was supposed to be the title of the exercise, and then we're starting a new sentence here. Sorry about that, I was confused. The grammar in my sentence wasn't making sense. So we're going to find the term for an investment to double, and now we're starting with all of our conditions. So a sum of $5,000 is invested at an interest rate of 5% per year. And this is our rate. So we want to find the time required for the money to double. If interest is compounded A, semi-annually, and B, continuously. So first we're going to start with A. So we're going to take our compound interest formula, so 5,000 times 1 plus 0.05 for 5% over 2 for semi-annually times 2t. And then for our money to double, that means we need $10,000. And now we want to solve for t. So first we're going to divide both sides by 5,000. So we get a 1 plus 0.5 over 2 raised to the 2t equaling 2. And now we're going to take the log of both sides. I'm going to use the natural log just because I like that one a little bit better, but y'all could use any amount actually, yes, y'all could use any log, base, whatever. I just like the natural log because it's one less letter to write, and for me, that's just really nice. So then if we have the natural log of 1 plus 0.05 over 2 to the 2t equaling the natural log of 2. Now using law of logarithms, we can bring down that exponent and we get 2t, the natural log of 1 plus 0.05 over 2 equaling the natural log of 2. And now we can divide both sides by 2 times the natural log of all of this jazz here on the left. So then we get t equals the natural log of 2 over 2, the natural log of 1 plus 0.05 over 2. And now using a calculator, this is approximately 14.04 years. So here would be a test quality answer. And here is a calculator, which is okay to do on the homework. You need both on the homework, but for a test, since there's no calculators, you'll just end with this kind of nasty looking term. Okay, and now we're going to do B. So using our continuous interest equation, we have 5,000 e to the 0.05 t equaling 10,000. We divide both sides by 5,000, so we get e to the 0.05 t equaling 2. And now this one will definitely want to use the natural log because our equation has e in it. So if we take the natural log of both sides, we end up with 0.05 t equaling the natural log of 2. And now we're going to multiply both sides by 0.05. And 0.05 is actually 1 over 20. So we're going to end up with t equaling 20 times the natural log of 2, which is approximately 13.86 years, which is definitely less time than 14.04. So it again shows us that continuously compounding interest is always a little bit better than compounding interest. All right, class, that's all that I have for you today. Thanks so much.